Hi, this is Paul from Tech. In this video, I will introduce a formula to find the initial value for doubling time growth model. Here is the formula we call initial value formula. To find the initial value, solve the doubling time growth model for P0. We can definitely find what is the initial value for P0. Okay. Let me draw a graph to show you the meaning. If I put this is the time, if this is the y value, and we know the doubling time growth model, let me put here is the initial value P0, because we know the model. Okay, let me draw the model like this way, grow, which means we know doubling time, right? We know TD, and we also know another future value, okay, PT. This we know, which means we also know the specific time T, but we don't know what is the initial value. We need to find out what is P0. This is the question. Of course, where is the P0? P0 is in this formula. We call the initial value formula. Okay, this formula, can you see something special? Okay, the base now is 0.5, no longer 2. They are different, right? And a little bit later, you will learn another formula we call the half-life decay. Exactly, this is a half-life decay model. Let me show you here the half-life decay model. But we need to look backwards. Okay, so if we look backwards, okay, what does it mean? If we take the future PT on this graph as the initial, and then look backwards, can you see? Okay, look backwards. Therefore, P0 in this half-life decay model, which is the future, okay, and we still need to find the future value for a half-life decay model. Half-life decay model is still exponential decay. We will learn this a little bit later. For this formula, I will prove it at the end of this video. But first, let's practice this formula. Here is the first question. Suppose that a certain city's population doubles every 12 years. If there are currently 10,000 people, how many people were there 34 years ago? Okay. First, we know the population grows exponentially because it says double every 12 years. We do have a doubling time, so there's a doubling time growth model. Let's look at the question. How many people were there 34 years ago? 34 years ago, which is the past time. Therefore, we need to find the initial value. Okay, let me highlight 34 years ago is the initial value. Or let me draw a graph to show why. Okay, like this. If this is the timeline, okay, is time. And currently, which now, right, so up here. And this point, initial point, see, is 34 years ago. 34 years ago. Okay, so usually the past time we set up as a P0. So if this value is P0, now here is the future value PT. Okay, currently should be the future value. And what is T? Of course, 34 years ago to now is 34 years, right? So we know T. See, we know PT, we don't know P0. Therefore, this is an initial value. So we need the initial value formula. Let me copy the formula here first. So P0 is PT times 0.5 raised to the power of T over TD. See, that's the formula we need. Okay, again, so let me find out all the parameters. What is PT? So PT is the future, right? The future, which is the current. Now, here, 10,000 is PT. What is T? 34 years ago, so this is T. What is TD? Double every 12 years. This is TD, doubling time. So we have everything, right? Per log. All the value into the formula. See, we have the initial value, P0 equals. PT is 10,000 times 0.5 raised to the power of. T is 34 years. TD is 12 years. Okay, and use your calculator to calculation. You will get it. This approximate 1,403. That's the answer. Which means 34 years ago, how many population? It's 1,403. Okay, let's practice one more question. Here is the second question. Suppose that a bacteria population doubles every 6 hours. You know this is the doubling time. So the doubling time growth model we have to use. If the current population is 40,000, how many bacteria were there 2 days ago? Let me highlight this. 2 days ago is a past time, similar as the last question. So we need to find the initial value, right? So this, we need to find the initial value. Let me copy the initial value formula again, which is P0 equals PT, the future, times 0.5 is the base raised to the power of T as the time, and over TD. Okay, let me highlight again. This is the formula we need. Okay, now let's find all the parameters. What is PT? PT is the population at this moment, right? Which is 40,000. That's PT. So we know this one. What is TD? 6 hours. Okay, so we get it. This is the doubling time TD. So we know. What is T? It says 2 days ago. That's exactly T. But be careful. Let me highlight. The doubling time is in hours. So T should be consistent also in hours. Therefore, we have to do a little change. See, D equals 2 days. We do need to change into hours. How many hours? 48 hours. Let me highlight. Okay, so T, we use 48 hours. So we look at it. All the parameter we have, right? Now, we plug all the value into the formula to calculation. So the initial value P0 equals PT is 40,000 times 0.5 raised to the power of T. We have to use 48 hours. TD, we have to use 6 hours. See, we have everything. Using our calculator to calculation, we get it. The answer is 156 around. That's the answer. Which means the population 2 days ago is 156. Okay. Now, let's prove the formula. Here is the proof for the initial value formula. Let's start from this formula, which is the doubling time growth model we do have, right? Let me write here. So PT, the future, equals P0, the initial, times 2 raised to the power of t over td. Okay, and in this formula, we need to do what? We need to find what is P0. Okay, which means we have to solve this equation for what? For P0. Okay, how to solve? Of course, we can divide the coefficient, which is this big number, to raise to a power both sides. Let me see. Okay, I divided it by this number to the right. Okay, again, I have to divide it the same number to the left, which is 2 raised to the power of t over td. Okay, now we can cancel this big number. So what do we get? We find the P0, right? There are 4. Now we have P0, which is this one. Is a fraction. Let me put this fraction again, which is a Pt over 2 raised to the power of t over td. This formula looks complicated. Okay, let's do this. The denominator is exponent. Over exponent, we can use the negative exponent, so goes to the numerator. So therefore, let me write here. Therefore, this we can write in this way, which is a Pt times 2 raised to the negative power. Therefore, there's a negative t over td. Let me put the parentheses again. Does this make sense? Or let me write here. What we used is a negative exponent. Okay, negative exponent, which means a raised to the negative power equals 1 over a raised to the positive power. We call the negative exponent. That's the definition. Can you see? Okay, after this, now what do we have? I can put this negative 1 to 2, the power of 2, which means the power rule we have. Let me directly put first. We can do a little change now. So here is Pt times, we do this 2 raised to the negative 1's power. Okay, and raised to another power t over td. Can you see? Negative power goes to negative 1 times that. That's what. Okay, if you do this, this is a power raised to another power. Okay, that's a power rule. Times together, the product is the power. Let me just put here. What we use is power rule. Okay, of exponent, which means a raised to the m's power raised to a power again is a raised to a new power, which means m times n, the product. Okay, now easy. We do have the formula now. Pt times 2 raised to the negative 1's power is 0.5. Okay, is 0.5. And then the power is t over td again. Or let me just write here, because 2 raised to the negative 1's power is negative exponent 1 over 2 raised to the 1's power. That's 0.5, right? Okay, so that's the formula. Okay, from the beginning, can you see here? And then equals here. Is this the formula we get? Yes, definitely. This is the formula, right? That's all. Thank you.